The Large Hadron Collider is one of the wonders of the modern world. It's believed to be the largest and most complex machine mankind has ever created.
In laboratories around the world, scientists have been uncovering strange anomalies that challenge our understanding of how time works. Experiments have revealed particles that appear linked across distance, clocks that tick differently depending on where they travel, and strange imbalances in how events unfold. If these discoveries are correct, then time itself may not be as stable as we once believed. Cracks in time. For most of human history, time was treated as something simple and dependable because every experience in everyday life suggests that it moves forward at a steady and predictable pace. A second feels like a second, a minute feels like a minute, and clocks placed next to each other appear to move in perfect agreement. Because of that, scientists once assumed that time flowed the same way everywhere in the universe, ticking forward like an invisible metronome behind every event that takes place. But during the 20th century, that assumption began to break down in ways that nobody expected. The first major cracks appeared when physicists began studying time with extreme precision using atomic clocks, which measure time based on the vibrations of atoms rather than mechanical gears or electronic circuits. These clocks are so accurate that they can measure time differences smaller than a billionth of a second, which allowed scientists to test ideas that had previously only existed as theoretical predictions. One of the most famous demonstrations happened in the early 1970s when physicists decided to test a strange prediction that had come from Albert Einstein's theory of relativity. According to Einstein, time is not universal and fixed the way people once believed. Instead, time can stretch or slow down, depending on two factors: speed and gravity. To test this idea, researchers placed several highly precise atomic clocks aboard commercial airplanes and flew them around the world. At the same time, identical clocks were left on the ground to serve as a control. After the flights were completed, the clocks were compared with each other. What they found was something that would have sounded impossible only a few decades earlier. The clocks that had traveled on the airplanes no longer matched the clocks that had remained on Earth. Some had gained time while others had lost time depending on the direction of the flight and the altitude of the aircraft. The difference was extremely small, measured in tiny fractions of a second, but it was exactly what Einstein's equations predicted. In other words, time itself had passed at slightly different rates depending on where the clocks had been. A clock moving quickly relative to the Earth experienced time differently than one that stayed still. At the same time, a clock higher above the planet's surface experienced slightly less gravitational pull and therefore ticked faster than one closer to the ground. These differences may sound small, but they prove something profound about the universe. Time does not flow at the same speed everywhere. This strange behavior is not just a laboratory curiosity either, because it affects technology that millions of people rely on every day. The satellites used by global positioning systems orbit thousands of kilometers above Earth while moving at enormous speeds, which means the clocks on those satellites experience time differently from clocks on the ground. Engineers have to correct for those differences constantly, because without those adjustments, GPS systems would begin drifting by several kilometers each day. But relativity was only the beginning of the strange discoveries involving time. As particle physics advanced and scientists began studying matter at smaller and smaller scales, they discovered behavior that was even harder to explain. Inside particle accelerators, subatomic particles are created, destroyed, and transformed in extremely short bursts of time, allowing researchers to study how the most fundamental processes in the universe actually work. In some of these experiments, scientists noticed something unusual about the way certain particles behaved when their reactions were examined in reverse. According to many of the traditional laws of physics, the equations that describe motion and energy should work the same way whether time moves forward or backward. If a process is filmed and then played in reverse, the underlying physics should still make sense. But in the early 2010s, researchers working with extremely large particle experiments began noticing an imbalance. Some reactions occurred more frequently in one direction than in the other. One of the clearest examples involves short-lived particles known as B-mesons, which are produced in enormous numbers inside particle accelerators. These particles exist for only a tiny fraction of a second before transforming into other particles, but during that brief moment, scientists can observe how they change over time. After analyzing billions of these reactions, researchers discovered something surprising. Certain transitions occurred more often when time moved forward than when the equations were applied in reverse. This phenomenon is known as time reversal violation, and it suggests that at the most fundamental level of reality, the universe may actually prefer one direction of time over the other. That discovery raised a difficult question for physicists. If the laws of nature do not behave symmetrically when time is reversed, then the forward flow of time may not just be a human experience or psychological illusion. Instead, the direction of time itself could be built into the structure of the universe. By this point, the picture of time had already begun to look very different from the one people had believed for centuries. Time could slow down depending on motion. Time could speed up depending on gravity, and certain processes in the microscopic world seemed to behave differently depending on the direction in which time flowed. These discoveries did not mean scientists had broken time or discovered time travel, but they revealed something just as unsettling. Time was no longer the stable background of reality that people once assumed it to be. Instead, it appeared to be something far more flexible, influenced by speed, gravity, and the strange rules governing the smallest particles in existence. And as researchers continued probing deeper into the structure of matter, they would soon discover anomalies even stranger than these. Experiments that broke. By the time physicists had confirmed that time could stretch and slow down depending on speed and gravity, the idea that time was perfectly stable had already begun to collapse. But the next set of discoveries pushed that realization even further, because they suggested that the behavior of time at the smallest scales of reality might not follow the same rules that we experience in everyday life. These discoveries began appearing inside particle accelerators, where scientists collide subatomic particles at enormous speeds in order to study how matter behaves at the most fundamental level. In these environments, particles exist for only tiny fractions of a second before transforming into other particles. But during that short window, researchers can observe processes that would never appear in the ordinary world. One of the most important breakthroughs came from an experiment known as the BABAR experiment, which operated at the SLUSY National Accelerator Laboratory in California. The goal of this experiment was to study particles called B mesons, which are unstable particles produced when high-energy collisions occur inside particle accelerators. B mesons are interesting to physicists because they change into other particles extremely quickly, which allows scientists to observe how certain transformations unfold over time. By producing billions of these particles and recording their behavior with highly sensitive detectors, researchers hope to test some of the deepest assumptions about how the laws of physics operate. One of those assumptions involves something called time symmetry. Many physical laws appear to behave the same way whether time moves forward or backward. If a simple physical process is filmed and then played in reverse, the motion still follows the same mathematical rules. A ball rolling down a hill can be imagined rolling back up the hill, and the equations describing the motion still make sense. For decades, scientists believed that the laws governing particle interactions would follow the same principle. But the results of the BABAR experiment revealed something unexpected. After analyzing billions of B meson reactions, researchers discovered that certain transformations happen more often in one direction of time than in the other. In other words, when physicists compared how frequently a reaction occurred moving forward in time versus backward in time, the numbers did not match. This meant that the process was not perfectly symmetrical. One direction of time was slightly more likely than the other. The effect was extremely subtle, but it was measurable and statistically significant, which meant it could not simply be dismissed as random noise or measurement error. For physicists, this was an extraordinary discovery. It suggested that time itself might have a preferred direction built into the laws of nature. That idea might seem obvious at first because human experience already tells us that time moves forward rather than backward. But the deeper implication is that this forward direction may not simply be the result of how humans perceive events. Instead, the asymmetry could be encoded directly into the structure of physical reality. Around the same time that researchers were studying time asymmetry, another line of experiments was producing results that were just as strange. These experiments involved a phenomenon known as quantum entanglement. For physicists, this was an extraordinary discovery. It suggested that time itself might have a preferred direction built into the laws of nature. That idea might seem obvious at first because human experience already tells us that time moves forward rather than backward. But the deeper implication is that this forward direction may not simply be the result of how humans perceive events. Instead, the asymmetry could be encoded directly into the structure of physical reality. Around the same time that researchers were studying time asymmetry, another line of experiments was producing results that were due quantum entanglement, occurs when two particles become linked in such a way that the state of one part is strange. These experiments involved a phenomenon known as quantum entanglement. Quantum entanglement occurs when two particles become linked in such a way that the state of one particle is connected to the state of the other, even when they are separated by large distances. When one particle is measured, the other particle immediately reflects a corresponding change, regardless of how far apart they are. At first glance, this behavior seems impossible because nothing is supposed to travel faster than the speed of light. Yet entanglement appears to create correlations between particles instantly. Scientists have tested this phenomenon repeatedly in laboratories around the world, and every time the results have confirmed that the connection is real. What makes this phenomenon particularly strange is that the relationship between the particles does not behave like a simple signal traveling from one place to another. Instead, the particles appear to share a single quantum state, meaning that their properties are linked even though they exist in separate locations. This raises difficult questions about how cause and effect operate at the quantum level. In some experiments, physicists have even designed tests where the measurement choices made in the present appear to influence how particles behaved in the past. These setups, often referred to as delayed choice experiments, explore situations where the outcome of a measurement seems to determine which path a particle took earlier in its journey. The results do not mean that information is literally traveling backward in time, but they suggest that the relationship between events may not always follow the simple timeline we experience in everyday life. Instead of a straightforward chain of cause and effect, the quantum world sometimes behaves in ways that appear to blur the boundary between past and present. Each of these discoveries challenges a different assumption about how time and causality are supposed to work. Individually, they might be explained as unusual quirks of modern physics, but taken together, they suggest that time may not behave like a simple, universal clock that ticks the same way everywhere. And as scientists began building even more powerful machines to explore these mysteries, they would soon encounter experiments that pushed these questions even further. CERN and the particle mystery. By the early 2000s, physicists had already uncovered several discoveries that made time look far stranger than it once seemed. But if scientists wanted to understand what was really happening at the deepest level of reality, they needed a machine capable of recreating conditions that had not existed since the earliest moments of the universe. That machine was built beneath the border of France and Switzerland. It is known as the Large Hadron Collider, or LHC, and it is the most powerful particle accelerator ever constructed. The collider sits inside a circular tunnel roughly 27 kilometers in circumference, buried deep underground, where it can operate safely while accelerating particles to extraordinary speeds. Inside this massive ring, beams of protons are pushed to nearly the speed of light using powerful magnetic fields. These beams travel in opposite directions around the circular tunnel until they are directed into head-on collisions. When those collisions occur, enormous amounts of energy are released in an instant, producing showers of new particles that scientists can detect and analyze. The purpose of these collisions is to probe the most fundamental building blocks of matter. By recreating extremely high-energy conditions, researchers can observe particles that normally exist only for tiny fractions of a second before disappearing. These short-lived particles provide clues about the deeper structure of the universe and the laws that govern it. Most of the time, the results of these collisions are chaotic and difficult to interpret because dozens of particles may appear and vanish within moments of impact. But hidden inside the massive streams of data produced by these experiments are patterns that reveal how the fundamental forces of nature operate. Over the years, some of those patterns have raised new questions about the nature of time and causality. One area of interest involves extremely short-lived particles known as top quarks, which are among the heaviest particles ever observed. Top quarks exist for such a tiny fraction of a second that they decay almost immediately after being created, which means scientists must analyze the products of their decay to reconstruct what happened during the collision. When pairs of these particles are produced together, physicists sometimes observe correlations between them that persist even after they separate and decay. These correlations suggest that the particles remain linked through quantum entanglement, even though they were created in extremely violent collisions and moved apart almost instantly. This type of entanglement occurs at energy levels far higher than anything previously observed in laboratory experiments, which means researchers are seeing quantum effects playing out under conditions that are closer to the early universe than to everyday physical systems. The deeper scientists probe these interactions, the more it becomes clear that the universe does not behave like a simple collection of independent objects moving through space. Instead, the underlying structure of reality seems to involve networks of relationships that extend beyond the straightforward chain of cause and effect that people experience in everyday life. Another reason the Large Hadron Collider attracts so much attention is that it operates at energy levels that allow scientists to test theories about the fundamental structure of space and time themselves. Some theoretical models suggest that space and time may not be perfectly smooth and continuous. Instead, they could have an underlying structure at extremely small scales, sometimes described as a kind of quantum fabric that governs how matter and energy interact. If such structures exist, then high-energy collisions could reveal subtle clues about how time behaves at the smallest possible distances. One of the most famous discoveries at the Large Hadron Collider occurred in 2012, when scientists confirmed the existence of the Higgs boson, a particle associated with the field that gives mass to other particles. This discovery completed a major piece of the standard model of particle physics and demonstrated that the collider could successfully reveal previously unknown aspects of reality. Yet even after this milestone, many of the biggest questions about the universe remain unanswered. Glitches in reality. Up to this point, most of the anomalies surrounding time have come from controlled scientific experiments. But outside of laboratories, another category of strange events has quietly gained attention over the years. These events are often described as glitches in reality, moments where people claim that something about time or memory does not behave the way it normally should. One of the most widely discussed examples is known as the Mandela effect. The term refers to situations where large groups of people remember something a certain way, even though historical records show that those memories are incorrect. The name itself comes from a false memory that circulated widely on the internet, where many people believed that South African leader Nelson Mandela had died in prison during the 1980s. In reality, Mandela was released from prison in 1990 and later became president of South Africa. But the number of people who shared the same incorrect memory led some observers to wonder how so many individuals could recall the same event that never actually happened. Since then, similar examples have been discussed across the internet and in psychological research. Some people claim to remember alternate versions of famous logos, movie lines, or brand names that do not match official records. In some cases, the differences are small details such as spelling variations or design changes that people insist they remember differently. Psychologists generally explain these situations as false memory formation, which occurs when the brain fills in gaps in memory using patterns that feel familiar. Human memory is not a perfect recording of past events. Instead, it is a reconstruction that the brain builds using fragments of information, expectations, and assumptions. Because of that, people can develop very strong memories of events that never happened exactly the way they recall them. But the reason the Mandela effect attracts so much attention is that some of these cases involve very large groups of people who share the same incorrect memory. When thousands or even millions of individuals report remembering the same detail differently, the phenomenon begins to feel more mysterious than a simple memory error. Some people have suggested that these shared memories could represent alternate timelines or changes in reality, although there is currently no scientific evidence supporting that idea. Most researchers view the Mandela effect as a fascinating example of how human memory works rather than proof that time has been altered. Still, the phenomenon highlights something important about the relationship between time and perception. Our understanding of the past depends entirely on the reliability of memory and records. If either of those sources becomes uncertain, then the timeline of events can appear far less stable than we usually assume. Stories about glitches in reality extend beyond shared memories as well. Over the years, many people have described strange experiences where events appear to repeat, skip forward, or change unexpectedly. These experiences are often shared online in communities dedicated to unexplained events, where people describe encounters that feel like brief breaks in the normal flow of reality. But even when these experiences can be explained by psychology, they still contribute to the growing cultural fascination with the idea that reality might not be perfectly stable. The reason these stories resonate with so many people is that they touch on a deeper uncertainty about how time and memory actually work. Every person experiences time through the lens of their own perception, which means the past exists primarily through recollection rather than direct observation. Over the years, many people have described strange experiences where events appear to repeat, skip forward, or change unexpectedly. These experiences are often shared online in communities dedicated to unexplained events, where people describe encounters that feel like brief breaks in the normal flow of reality. But even when these experiences can be explained by psychology, they still contribute to the growing cultural fascination with the idea that reality might not be perfectly stable. The reason these stories resonate with so many people is that they touch on a deeper uncertainty about how time and memory actually work. Every person experiences time through the lens of their own perception, which means the past exists primarily through recollection rather than direct observation. Because of that, even small inconsistencies can create the feeling that something about reality has shifted. Scientists studying memory and perception continue to investigate how the brain constructs its sense of time and sequence. Research shows that the brain constantly organizes experiences into narratives, placing events into an order that makes sense based on context and expectation. When that narrative breaks down, even briefly, the result can feel like a disruption in reality itself. And the more researchers examine time and memory, the clearer it becomes that time itself has behaved in ways that push the limits of our most advanced theories. The places where time breaks. If the earlier discoveries suggested that time was more flexible than scientists once believed, the most extreme environments in the universe push that idea even further. In certain regions of space, the flow of time becomes so distorted that the normal relationship between cause and effect begins to break down. These environments exist far beyond the laboratories and particle accelerators on Earth, and they reveal just how unusual time can become when the universe reaches its most extreme conditions. One of the clearest examples comes from objects known as black holes. Black holes form when extremely massive stars collapse under their own gravity at the end of their life cycles. As the star collapses, its mass becomes compressed into a region so dense that the gravitational pull becomes overwhelming. At a certain distance from the center, gravity becomes so strong that not even light can escape. That boundary is known as the event horizon, and once anything crosses that boundary, it can never return. The reason black holes are so important to the study of time is because gravity does not only affect objects moving through space. Gravity also affects the rate at which time passes. Einstein's theory of general relativity predicts that the stronger the gravitational field, the slower time moves relative to an outside observer. Near extremely massive objects, time begins to slow down dramatically. This effect becomes especially noticeable near the event horizon of a black hole. From the perspective of a distant observer watching an object fall toward a black hole, something remarkable appears to happen. As the object approaches the event horizon, it seems to slow down more and more until its motion nearly stops. The light coming from the object becomes stretched and dimmer, and the object appears frozen in time just outside the event horizon. But for the object falling toward the black hole, the experience would be very different. To that observer, time would feel normal, and they would continue falling past the event horizon without noticing any sudden change. This strange difference in perspective highlights just how flexible time becomes in extreme gravitational environments. Two observers watching the same event could disagree about how much time has passed. Black holes also introduce another mystery involving something physicists call the information paradox. According to the laws of quantum mechanics, information about physical systems should never be destroyed. Every interaction in the universe should leave some trace that could theoretically be reconstructed. But black holes appear to challenge that rule. In the 1970s, physicist Stephen Hawking discovered that black holes are not completely stable objects. Instead, they slowly lose energy by emitting tiny amounts of radiation, a phenomenon now known as Hawking radiation. Over extremely long periods of time, this radiation would cause a black hole to shrink and eventually disappear. If a black hole eventually evaporates, the question becomes unavoidable. What happens to the information contained in everything that fell into it? If that information disappears permanently, then one of the most fundamental rules of physics would be violated. But if the information somehow survives, scientists still do not fully understand how it escapes from the black hole. This paradox has forced physicists to rethink the relationship between time, space, and information itself. Another place where strange time-related anomalies appear involves spacecraft performing gravitational flybys around planets. When spacecraft approach a planet, they can use the planet's gravity as a slingshot to increase their speed and change direction without using additional fuel. Engineers calculate these maneuvers with extreme precision, taking into account every gravitational force acting on the spacecraft. But in several missions, something unusual occurred. Spacecraft performing flybys around Earth emerged from the maneuver with slightly more speed than predicted. The difference was extremely small, only a few millimeters per second, but the anomaly appeared consistently in multiple missions, including spacecraft such as Galileo, NEAR, and Rosetta. Despite careful analysis, scientists have not yet found a single explanation that accounts for every instance of this phenomenon. Some researchers suspect subtle effects related to Earth's rotation or gravitational field, while others suggest that unknown factors in spacecraft motion could be responsible. Regardless of the explanation, the anomaly demonstrates how even well-understood gravitational systems can still produce unexpected results. When scientists compare all of these discoveries together, a clear pattern begins to emerge. Time can slow down depending on gravity and motion, and the most extreme regions of space distort time in ways that challenge our deepest theories. For centuries, people believed time moved forward in a smooth and predictable way. But as scientists continue investigating these mysteries, the more they realize that our understanding of time could be the beginning of a much larger story we are not prepared for.